Okay. There I am. So, lecture 5-2. Curl, line integrals, and circulation. We'll start off with line integrals, shall we? Consider a curve C in a Euclidean vector space R3. Let R, components x, y, and z, be a parametric representation of C with the parameter variable t. Furthermore, let f be a map from R3 to R3, a vector-valued function of R, and let R prime be the tangent vector. The line integral is 5.9, which integrates f along the curve. Okay, that's the line integral. I know you guys have seen them before. If you want to refresh on computing line integrals, see the Shea, Divgrad, curl, and all that, and the Kreisig text, chapter 10. If f, the function we're integrating along the curve, is a force being applied to an object moving along the curve, the line integral is the work done by the force. More generally, the line integral integrates f along the tangent of C. Okay? That's the good old-fashioned line integral. Circulation. Consider the line integral over a closed curve C. Closed curve. What is a closed curve?
The end and the starting point are the same.
Right, exactly. So the starting point and the ending point are the same, comes back onto itself. It's denoted by the same expression, but with a circle, or sometimes an oval, around the integral. We call this quantity the circulation of f around C. For certain vector-valued functions f, the circulation is 0 for every curve. In these cases, static electric fields, for instance, this is sometimes called the law of circulation. Okay. Now we saw that one of the governing equations from lecture 5.1 of these types of systems that are described by vector fields is the continuity equation. Okay, the continuity equation gives us a governing equation. This line integral, the circulation, especially when it's equal to some quantity that we know from some sort of physical principle, like the fact that it's 0 for a given field, gives us another sort of governing equation for that physical system. So in those cases when it's equal to 0, for instance, sometimes we call it the law of circulation. It's not a super common term, but Shea uses it, and I think some other sources do as well. Brings us to the curl. Consider the division of the circulation around a curve in R3 by the surface area it encloses, delta S. So if you do a circulation integration and you divide it by the surface that it encloses, the surface area that it encloses, you get expression 511. In a manner analogous to the operation that gave us the divergence, let's consider shrinking the curve to a point and in the surface area, so shrinking the curve to a point and the surface area to 0. So when we bring that curve down to a point, the surface area that it encloses also goes to 0, and we get this expression 512, which is the limit as s goes to 0 of the circulation divided by the surface area. We call this quantity the curl, so the scalar curl of f at each point in R3 in the direction normal to delta S as it shrinks to 0. So as it shrinks to 0, even if your curve is not on a plane, as it goes to 0, as it shrinks to a point, it will be approximated better and better by a surface, a planar surface. And we will get the curl in the direction of the normal to that surface. Okay? Taking 3, or if you're in Rn, taking n, scalar curls in independent normal directions, enough to span the vector space, we obtain the curl proper, which is a vector-valued function curl, which maps from R3 to R3. So the curl in 512 is the curl in some direction, the direction normal to delta S as it shrinks to 0. You have to do 3 independent directions in R3 in order to get the vector curl, if you're going to use this integral definition of the curl. Okay, because the integration here is scalar, so you get out a scalar value. The curl is coordinate independent. Okay, we like things that are coordinate independent. In Cartesian coordinates, it can be shown to be equivalent to the following. So we have the x component being dfz dy. So the z component of f is differentiated with respect to y. We subtract from that the y component of f differentiated with respect to z, and it's similar for the y component, similar for the z component. So there's this thing where people try to remember this formula by using this cross product thing, but then you got to remember how to do the cross product of a 3x3 off the top of your head, which I don't know about you, but I always have to look up the minus signs, where those minus signs show up. So I don't really find that useful. It turns out that you can use a sort of right-hand rule for doing this. This is the way I try to remember it. If you've got a right-handed coordinate system, which we're always assuming, we've got x, y, z, then the x component here, you're going to take partials with respect to the other 2 components of f, right? So the x component has to do with the z and y components of f. So you know that. So you take the partial with respect to one variable of the component in the other direction. Okay, so the y and the z show up together, and the z and the y show up together. So you just got to figure out which one has the minus sign. You're adding them together, you got to find out which one has the minus sign. And the way that I remember this is just using the right hand rule that sort of reminds me that if you put your fingers in the direction of y to start, so y, and then you go to the partial with respect to z in the z direction, x is what comes out. So the x component, put your thumb in the x direction. I don't know if I could do that so that it actually makes sense on there. This way. And you do this rotation. It goes from y to z. So you take the partial with respect to y. You subtract the partial with respect to z. That works for each of these components. In the y direction, you have to take the partials of fx and fz to figure out which one is positive, which one is negative. You put your thumb in the direction of y. And you see that you go z to x. So the partial with respect to z comes first, then you go x, and you subtract the x. That's how I remember it. There's just any mnemonic that works for you is fine, or you can just look up the formula every time. But what does the curl of f represent? Okay, so we defined it in a sort of integral way, shrinking this circulation down to 0 to a point. So if f represents a fluid's velocity, so more generally, it quantifies the local rotation of f about each point. The local rotation of f. So f is a vector-valued function or a vector field, and the local rotation. Remember, we had the divergence, which was the local movement, the local sort of you could say field balance, right? In minus or out minus in, right, of the field. Well, for the curl, it's the local rotation, okay, as it shrinks to that point. So if you imagine a fluid that's going along and you have an element that shrinks down to nothing, you can think of the swirliness of the fluid. We had a bird hit the window. The swirliness of the fluid near that point as it shrinks down. So in a fluid, so if F represents a fluid's velocity, curl is the local rotation of the fluid about each point, and it is called the vorticity. So in your fluids class, you probably heard that term thrown around a little bit.
We didn't include this curve concept inside the vorticity.
Yeah. Well, that's how you compute the vorticity, is computing the curl of the velocity field. Yeah. Great. So, zero curl, circulation, and path independence. This is the thing I added right before the lecture started. Okay, circulation. It can be shown that if the circulation of F on all curves is 0, then in each direction n, and at every point, the scalar curl of F is 0, okay, in the direction n. In other words, if you take n dotted with the curl of F, you get the component of the curl of F in the n direction, and that equals 0. So this is the most complete way of writing it. Conversely, for the curl of F equals 0 in a simply connected region, F has 0 circulation. A simply connected region is a region for which every curve that you draw, every closed curve that you draw, you can shrink it down to a point without leaving that region. An example of a space that's not simply connected is a toroid, so like the donut. So if you were to take a look at the donut, and you drew a curve like this, a closed curve. See? You can't shrink that down to a point because it's going to get stuck on the hole, essentially. That's the issue. If you had a curve on a sphere, even if it was around a great circle of the sphere, but it's hard to draw that, so I'll just draw, I'll draw it. Okay. You could shrink this down by going off to the side, right, one side or the other, and you could bring it down to a point, but you can't do that for something like a toroid because of that hole in it. And this has to do with topology, right? This is the study of topology, like how spaces are connected to themselves and to each other and all that. So for a simply connected region, we can go the other way. So the way that the logic works is 0 circulation. So if we ignore the qualifiers of like at each point and in the normal direction, blah, 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 we can say 0 circulation implies 0 curl. 0 curl and the fact that we have a simply connected region implies 0 circulation. So you have to have both of those. It doesn't just go 0 curl to 0 circulation. You also have to have a simply connected region. So that's the little caveat there. Path independence. It can be shown that if the path integral of f on all curves between any 2 points is path independent, then in each direction n, and at every point, the curl of f is 0. In other words, for any n dot curl f is 0. Conversely, for curl f equals 0 on a simply connected region in each direction n and at every point, f, all line integrals are independent of path, which is not generally the case. So we have to have that simply connectedness again. And so we have, once again, we have path independence implies zero curl, and the fact that you are working in a region that is simply connected gives you path independence. Okay, path independence is nice, right? It doesn't matter how we go from one point to another point. If the integral is the same, no matter which path you take between those 2 points, that's a nice thing for computation. It also has some interesting physical implications for different systems that have this property of path independence. And the one that Shea uses is the electric field, but there are others. Now, would a fluid that can just move generally, a general fluid motion, is that going to have its velocity? If f is the velocity of the fluid, distributed fluid, is that going to have path independence? No. And the curl can be non-zero, right? So any sort of vorticity that shows up. You can have fluid fields that happen to be have no vorticity in them, but that is not generally the case. It's not the case for all fluid flow. Yeah. Okay. Exploring curl. Oh, I did at the very end, and I didn't get a chance to put it where it belongs in here. I started drawing a little diagram of the relationships here. Whoop, whoop, whoop. Okay, so we have path independence and zero circulation essentially are equivalent, okay? You can have, if it's path independent, there's zero circulation. If there's zero circulation, it's path independent of the line integrals. Zero circulation implies zero divergence. Path independence implies zero divergence. It does not go the other way, though. You have to have something more. You have to have that and. You also need to have the simply connected region. So we can't go back unless there's a simply connected region. I didn't quite know how to put that on this diagram. This is called an implication graph, and I was digging into that while I was giving an exam in the last period. But anyways, it's pretty fun. So that figure is probably going to get better, but that's just breaking it down. For me, a little summary diagram is very helpful. Okay, so let's explore this. So curl is perhaps best explored by considering it for a vector field in R2, such that a field in Cartesian coordinates has this curl. Wasn't really a complete sentence, but whatever. So we're going to have 0 in the z direction. And z direction shows up here as well. The partials with respect to z will also end up being 0, so we end up with just this expression for the curl in the plane. And it always ends up being in the normal direction to the xy plane, in the k direction. Okay? If we overlay a quiver plot of f over a color density plot representing the k component of curl, we can increase our intuition about the curl. At least that is what I claim. Okay, so same sort of setup as previous lecture, where we have a symbolic Python notebook here, and we're going to use the same function, quiver plotter 2D, from lecture 5.1. I did do a couple little updates, like there was that error, and I also added some functionality that allows you to have constant directions in your field, so that your vector field can have a constant or 0 in one direction without it throwing an error. So I fixed that bug. But so you can look, I did update it. It's in the previous lecture now, correct, in the correct form. So the first one I want to look at is actually if the x component of the field is 0 and the y component is cosine 2 pi x. So this is essentially a vector field that's shown here. There's never any, if this is a fluid, there's never any x motion. It's all just moving in the y, right? And the speed at which it moves in y is a function of x. It's a sinusoid. So we have, if you are going from left to right, you have this sort of the sinusoidal, specifically cosinusoidal form of the velocity of say fluid particles in the example of fluid. And so what you'd think of here is if you put a like a water molecule here and you were going to follow it, it would move straight up like this at a pretty high rate, relatively high rate. If you put one right here, it would also move up, but it would move up slower, right? It would be lagging behind because the field in the middle here is going faster. So it's going to have moving fast up there, and then in these other regions, you're going to have it moving fast down. Okay, so we're going to look at the curl with the density plot. The curl, remember the curl is in the z direction, it's in the k direction, it's out of the board, positive, into the board, negative, and the positive ones are green, and then the negative curl is magenta. And what we see is, first let's look at where there's no curl happening, which is right in these regions here, right at the peaks and the valleys of the sinusoid. So at the peaks, we're looking for a difference in two side-by-side, a sort of shearing of the fluid, okay? That is the vorticity, that's the sort of local rotation that's happening. So if one is moving faster than the other, even if they're going in the same direction, if one's moving faster, so you can see as my pen here, so like it like rotates the pen, right? There's a sort of a local rotation that happens when one moves faster than the other, even if they're both moving in the same direction. Clearly, if they're moving in opposite directions next to each other, you're going to get some local rotation. But even if they move in the same direction, if one's faster than the other, we'll have some curl. But when you hit that peak, you get this symmetry among the two sides, right? So locally, you're going to approach a perfectly equal velocity on each side as you shrink this down. So you're going to end up with no curl at the peaks of the velocity here. Okay, let's look at the crossover here. And so what's happening here is we have vectors locally, and as you zoom in, you can imagine this would continue to be true. You'd still have, as you zoomed in more and more, you'd still have on the right hand side of the board, if you put your fingers in that direction, you have this positive upwards flow, and then the other direction you have this negative flow. So you have this action here. Well, actually, if we're going to go with the direction of my fingertips being the direction of flow, it's like this, right? Some's moving up, the other's moving down. And as you shrink it down locally to that point where there's a little bit moving up and a little bit moving down, they're going exactly opposite each other. and we have maximum vorticity, maximum curl. And the direction is actually put your fingers around in the direction of the arrow pointing up and then pointing down. And the right-hand rule tells us that it's positive curl in the K direction. Okay, if you go to one of the negative ones, you have the same sort of thing happening, but now we have, going into the board here, a leftward, left goes up, right goes down, and your right thumb goes into the board, so you have a negative vorticity or negative curl. Okay, so that curling action, the curling and the swirling, if you were to look at a curve, a closed curve here, you would have things swirling around in this direction, right? And as you shrink that down, it continues to be truer and truer, that one side goes up, the other side goes down, etc. So we've got this non-zero curl that's happening. We see that. So we have fluid flowing. Broadly speaking, we have channels of fluid flowing up and then channels of fluid flowing down. And in between those two, we get a lot of vorticity. We get a lot of curl. Okay. The next one, so the curl we compute, and it's just, using that formula, it's pretty easy. Take a couple partial derivatives, add them together, and then get that. The next one we want to do is a field that's 0 in x and then x squared in y. So we get this, once again, we have no fluid flow or no vector direction in the x direction, only in the y direction. And it depends on x. So there's very little flow in the center, and you have more and more flow. And that more and more flow, it's not increasing linearly, it's increasing quadratically. So what that means is if you look at two adjacent arrow tips, and it's a little hard to see, if you look at two adjacent arrow tips down at low, small values of x, the difference here in arrow length is smaller, and as you go, the difference in arrow length gets larger. Okay, and that means that you have the situation of both moving in the same direction. Like you think of fluid, where like you have everything's moving in the same direction, but it's moving faster the further out you go. So the outer one is surpassing the outer. So if you put a particle here and a particle here, this outer one's going to move vertically faster than this one's going to move. This one's going to move slower. So the outer one's going to be bypassing it, and there will be that sort of local shearing happening, and that's the vorticity again, where we've got the curl being non-zero. Okay, it's positive here because the outer one is greater than the inner one, so you get this direction of curl. On the other side, everything's still moving in the same direction, but the stuff on the left is moving faster than the stuff on the right, so it's going to cause a curl into the board. Okay. If this increases linearly, so back over on the positive side, if this increases linearly, what's the curl going to be? Constant. Yeah. It's going to be constant because there is still, outer one is still going faster than the inner one, but it doesn't, that curl doesn't increase as you go out. It's the same delta between each one, right? That same difference in vector length between each one. So you get a constant curl through the entire region. And I didn't plot those because they don't have really interesting, I do plot one at the end. They don't have density plots that are interesting, right? Because they're just constant. So I like the watermelon plots. They're pretty. So Okay. Great. Let's say the x component is y squared and the y component is x squared. Okay? I did a pretty sparse vector field representation here. The quiver plot's pretty sparse, but so that you don't get too much going on in one plot. And I wanted to have a good view of what happens locally. So what happens locally in the center here, like so if you go along this white band in the middle, you're going to have zero rotation, right? Zero curl. And so what's happening is the vector arrows have the same length and direction that are adjacent to each other, or they're very similar, right? So obviously there's a little space in between them, so they shift slightly, but they don't have a significant difference between them. One's not going much faster than the one that's right next to it. Right on that center of that stripe, you actually have a crossover where it's perfectly zero. So you'll have as it goes to zero, there'll be a perfectly parallel line, same length on each side. And what we've got as you go out, so if you go out, say to the right here, we're getting further and further away from being exactly parallel and the same length next to each other. We're going to end up with this outer side going faster than this inner one, and we're going to get a local curl, a local rotation, positive. On the other side, and you can see this a little bit better maybe, you see that these arrows that are next to each other are much different lengths, okay? And you'll get the outer one curling around the inner one, or shearing past the inner one, you could think of. I like to think of fluid moving around. I think that using that concept of shear, of slipping from mechanics of materials is also useful. That shear concept. So that's our x squared, y squared vector field. And you see that you have these, increasing vorticity, increasing curl as you go out from that y equals x band. Okay. Now let's look at one that's just fx. The x component is negative y, and the y component is x. Okay, so this is a rotational field, right? So we look at the vector field plot, and it's rotational. This nice swirling motion. And of course, these outer arrows are getting larger, right? The inner arrows are smaller, the outer arrows are larger. So if you just look at like one quadrant here, we have these sort of constant length vectors that are happening in like in a constant circle. Okay, they have constant length in a circle. But then the next circle out from that is going a little faster, and the next circle out from that's going a little faster. Next circle out from that's going even faster, right? The important thing here is that the difference among those, like the speed up for each increment outward, is the same. Okay, so there's a sort of linear increase in r of the speed, and when that happens, there is shear among each of these layers you could think of, but it's constant. So this one's bigger than this one, which is the same amount bigger than the one that's inside that, and so they have the same increase as you go out. Yeah. So that's the rotational field, you could call it linearly rotational field.
You can call it the one that really from the middle one is the offset of the other one.
Yeah, the offset is equal. Like the increment as you go from one to the next to the next, the increment's the same in speed as you go out.
But this increment is leading from one.
Yeah, the increment's the increment is constant. The increase is linear. Okay, so that's the curl. So this field has a curl to it, but it's constant, and it was equal to 2. That function computes the curl and returns the analytic value, and it was 2, and so it's constant everywhere. So everywhere you go, if you just put a dot down, the local rotation, the local curl is 2, and it's positive also, right? It's out of the board. Yeah. Okay. That's curl. That's path integrals. That's vorticity. That's path independence and circulation. Quite a few little concepts there covered. Okay. I encourage you to play with this. I mean, you can just like copy the Python code over and just start plugging in your own vector fields and see what happens.
So what is the use of curl again in studying engineering?
Yeah, so curl shows up a lot in fluid dynamics. So when you look at vorticity, it also shows up in mechanics. So solid mechanics, it shows up as like the rotation of a body. And pardon? Yeah, so in robotics, when you describe the dynamics of your robot, it shows up a lot in that. So the dynamics of really most things end up having most complicated things end up having vector fields associated with them, and the curl is meaningful in almost every case. The curl might be 0. And that's like the case for in electricity and electromagnetism for a static electric field. The curl is 0, and that's an important insight as well. So having the curl be 0 in a field is important because, you can show several things. For instance, you can test to see, is this a potential electric field, and you find the curl for it, and if it's non-zero, the answer is no, it can't be an electric field. You can also deduce what the electric field is, starting with these concepts. So it helps to also have Stokes' theorem, which I hope to give a little lecture on, maybe over the weekend, I don't know, Monday. Just have class tomorrow. Yeah. All right. Any other questions? I know we got to get to the thesis talk. So, all right.